Yeah, so as I was saying, it's great to be here in person. It's a beautiful campus after a long time. I'm going to be talking about this topic of auto bidding and allocations in ad auctions. Um, uh, First, just a quick comment on our team in Google Research. So our team is called Market Algorithms. We do multidisciplinary research in algorithms optimization, but also microeconomics, auction design, mechanism design, and connections to machine learning. This is a research which leads to product impact, products which give rise to new research problems. So it's a kind of very exciting area to be in. So advertising takes many forms on the internet, display ads being one of them. I'll kind of focus on this prototypical example of sponsored search advertising. So if you're on Google and you're looking, people go on Google to look for information, but they also go for with commercial intent, for example, for these different kinds of queries. And then what we do is we kind of connect the users looking for such kind of commercial intents with sellers who have these products or services to sell. Right. So this is a market essentially. It connects buyers to sellers, and as you know, it drives a lot of transactions, a lot of revenue, and this ad revenue supports the organic services that we provide, as well as the free kind of internet provides for the users. We look at a few different very specific aspects of this market design. The entire design is a pretty kind of big field. Mainly in this talk about around bidding and allocation. Here's kind of a quick overview. Right? So I'm going to talk about a few different results over here, and these are related under kind of a larger umbrella. I'll first talk about actually a very old result of ours on online budgeted allocation. And then fast forward to kind of recently where we've found some machine learning connections to somehow rediscover these algorithms in a different way, which is kind of pretty interesting. And then I'll talk about a different way of looking at kind of the similar problem, which is called the auto bidding framework. Talk about algorithms and equilibrium over there. And if there's time, I'll talk about some recent work which connects low regret machine learning algorithms to bid into these auctions. Okay. So here's, and feel free to ask any questions during. So let me start off with this notion of allocations over auctions in the presence of budget constraints. So I'll explain what this exactly means. Let's first look at how advertisers bid into these auctions online. Right? So here's I gave this example in the previous slide of a math tutor who was kind of selling her services to teach math to kids in the local area. Right? So they can enter into the platform a whole list of keywords which they think are related to their services and a bid per click. So what they're saying is that if someone in this local area searches for a high school tutor, please show my ad, and I'm willing to pay up to $10 per click on this ad, right? And then so on for the other keywords. And all the advertisers put in these bids at scale for all these different heterogeneous products that we have. And then when someone actually does a query for math tutor near me, then an auction runs at that point online, takes in the bids from all the different advertisers who are bidding on that keyword, and then an auction is run. Typically, it's like a second price auction, like a VCG auction or GSP auction, if you're kind of familiar with that. And then we decide which ad to show and how much do they pay upon a click, right? And in this talk, we won't worry too much about the auction design itself. That's a whole different talk, and a lot of interesting work over there. We will worry about a different aspect of this, the budgeting and bidding aspect. Right, so now if you think about this setting, then every time a query comes in, you have these different advertisers bidding on it, you run this auction, you find an ad to show, and you charge for it. So as I described that, that's a pretty stateless kind of system. It can run in parallel, and that's kind of the basic core of it. But there is another bidding component, which is this thing called the budget. And what the budget says is that this advertiser says, I'm willing to show an ad for the keyword math tutor. I'm willing to pay $5 per click, but I don't want to spend more than $100 per day. That's my budget. Right? And sometimes these bidding components can be mismatched. For example, you might have 100 potential clicks during the day for math tutor, and if they're going to pay on an average of $5 per click, that will result in a $500 of spend, but the budget is only 100. And this can happen for all the advertisers. So the platform has to do something to kind of take care of this. Right? So here's kind of one picture that you have all these little auctions running at the bottom layer. These are kind of the stateless auctions. That's where all the kind of auction design, mechanism design happens. And then we need this allocation layer above it, which kind of determines which ads, which bidders participate, with what bids do they participate. So you can think of it like some kind of an admission control layer on top of these auctions. And that's kind of a pure optimization side. A very simple allocation layer is just run the auctions, and as soon as someone finishes their budget, take them out for the day. And like that's the kind of the basic thing you would do. That has certain disadvantages, all related to the spend being very much clustered at the beginning of the day. So you start spending your money, and then by noon you spend your money, and then you're out of. You don't get kind of the queries for the rest of the day. Another method would be somehow spread out your spend, kind of pace it during the day. And the question is, like, how would you do this in an optimized manner? So this is from many years ago. We came up with this formulation, an abstract formulation for this problem, joined with Saveri and Vazirani. Umesh, of course, is here at Berkeley. Where you think of this bipartite graph on the right, there are n advertisers, and each advertiser has a budget. And then there are m queries or ad opportunities that arrive online as users start searching for things during the day. And when a query arrives, then you see the different bids from the different advertisers according to their bidding tables, and you have to decide which ad to show. Right? And it's kind of the basic way to show it is just run the auction for that ad. So in this case, you would, if you ran a simple auction, you would give this ad opportunity to this advertiser who's bidding 2, that's the highest. Of course, when an advertiser finishes the budget, then they can't participate anymore. So you need to somehow do something smarter. Okay, so what I didn't mention is that when you choose an advertiser to show an ad for this query, they will deplete their budget by some amount. Let's just assume that it's exactly the bid that you put in. Think of like a first price auction or something like that. And the goal is to, at the end of the query sequence, maximize the sum of the values that you matched, or equivalent to maximize the kind of total revenue out of this matching system. So if you think of this picture and you say all the budgets are just 1 and all the bids are either 0 or 1, that becomes this online bipartite matching. You match each vertex once, and so this is a generalization of that. And there's a beautiful paper by Karp and Vazirani even longer ago, which talks about bipartite matching. So what's the core problem over here? So the core problem is captured in this very simple advertiser query graph. It's just a 2x2 graph. 2 advertisers, budgets 100 each, and then there are 2 types of queries, and 100 copy of each arrive. So first, these queries arrive, and 100 of them, and the first advertiser bids 99 cents. The second one bids $1. And then at the end of it, this set of queries are going to arrive where only one advertiser is interested in it, which is the second advertiser. Right? So if you ran kind of the basic auction, give the query to the highest bidder, then you would allocate all of those 100 to the second advertiser because bidding a little bit more. And then, of course, you can see that they would exhaust their budget at the end of this phase one. And then you cannot allocate any of the second type of queries anymore. Right? Because the green advertiser there has now finished its budget. So if you call this like the greedy solution or kind of the basic auction, then you would get about half of the maximum potential. Because, of course, the maximum is to match the first set of queries to the first advertiser, get $99 for those, and then the second set to the second advertiser. Right, just match along the horizontal edges. So what can you do to kind of improve over this? So if you think of even the offline, like suppose you knew all the queries in advance, then even then that's quite a general problem. You have to think of some kind of a max flow or it's a packing LP, quite a general packing LP that you have to solve. So can we even imagine solving this online in a very kind of quick and elegant manner? We know that the simple method kind of does well, it gets you about a half. Can you improve on top of that? And so this is the algorithm that we came up with, which is during the algorithm at any point in time, define the spent fraction of advertiser A as the fraction of A's budget that's already spent by the algorithm during the matching. And then when the next query arrives, you allocate it to the bidder who maximizes not just the bid, which is the regular kind of auction, but some scaled notion of the bid. Okay, so the bid which is scaled by this function psi of the spent budget. And that function is basically this function here. So it's some kind of an exponential decreasing function where if you haven't spent any of your budget, then your scaling function is 1. So you participate with your full bid. As you spend more and more of your budget, your scaling function goes down so that now your bid has to be much higher to compete against other bidders who have not spent. Right? So you can see that intuitively is doing the right thing if you think about this zigzag graph. So what we could prove there is that this kind of very simple generalization of the basic auction achieves this competitive ratio of 1 minus 1 over E. And in fact, this is an optimal online algorithm. So no kind of, you could think of kind of, remembering many things about the past, try to predict many things about the future, but this kind of very almost stateless algorithm gets you the optimal performance. It's a mild variant of the basic auction, as I say. And what does it basically do? It trades off high bids with kind of high availability. So very simple idea. It's a worst case guarantee, this 1 minus 1 over E. So that no matter what the sequence is, you will achieve at least 1 minus 1 over E compared to the best you could do offline. And so at the end of the sequence, you could go back and kind of reallocate. You will still get about 63% of that. Right, so what does it do for our kind of very simple toy example? And the first set of queries arrive, like the first query will definitely go to the second bidder. But pretty soon, the first bidder will be more attractive because its bid is almost the same and it has spent less. So overall, it will just balance out the first set of queries between the two bidders. And then you have kind of space for the second set of queries. At least half of them will be allocated to the second bidder. Right? Was that clear? So you get 3/4 in this example, and then in general you can show that it's at least 1 minus 1. So where do these kind of these bid multipliers come from? So here is one interpretation from these two papers. That if you think about the problem, as said, it's a kind of a packing LP. So that's the primal problem. You want to kind of not spend more than the budget, but you want to maximize the total amount. You can write as dual. And if you had the entire sequence in advance, then the optimal dual variables provide the correct bit scaling functions. So those are like shadow prices. You can imagine that. Right? And our problem is online, so we don't have the entire LP at all. And so what kind of this algorithm does is it maintains some kind of an optimal online estimate of this optimal dual for all possible futures. So that's kind of the idea. So these alphas are one dual variable per advertiser, and that becomes the bid multiplier. So there's a lot of work in this area, like after this algorithm. And kind of one thing I want to highlight is that we designed the algorithm for this kind of worst case performance. And you might ask, well, you're not necessarily going to get a worst case in practice. You might have a lot of estimates of what's going to happen in the future. Or you might know that the queries are coming from some distribution, like IID or random order. So can we do better? And the intuition is that, well, so those bid multipliers, which are a function of the budget spent, were some kind of online estimates of those duals. Maybe we can get better online estimates if the input is coming from some distributional setting. And that's also kind of practically very implementable because you could use some kind of controller to estimate those duals. So there are two algorithms. One came pretty early, which said that, well, if the query sequence is coming from some distribution, then I'll just sample an initial segment of the distribution. And then I'll have a little LP over there. I scale down all my budgets by that amount. I'll take the small LP, find the optimal duals for that small LP, and then I'll use those optimal duals for the rest of the sequence. And that simple idea does work. And then kind of more recently, or a few years ago, a bunch of set of authors, but Agrawal Devanur in particular, found a very nice connection to solving LPs online using multiplicative weight updates or experts learning, where you have one expert per advertiser. And as the query unfolds, you update the weights on that expert, as well as use those weights to make your allocation decision. As I won't go into the details of that, but essentially there's a way of updating those optimal dual variables using experts learning. And so that's a very elegant algorithm. And both of these algorithms achieve a very close to one factor approximation, as long as the queries are coming in from kind of a fixed distribution or a random order. And so they can achieve 1 minus epsilon for kind of any constant epsilon. And there's a lot more work in kind of this whole allocation algorithms direction. This is just a sample. I wrote a survey, and now it's already quite old, but it has a bunch of these different directions over here, which are very interesting. Okay, so fast forward now to a few years ago. When with some co-authors, we asked the following more general question, not even related to this topic. This was when the machine learning revolution, had proven its great value in problems such as vision, machine translation, and so on. And the question we asked is, can machine learning help us discover algorithms? And so, what does that mean? So, okay, and so this is based on these two papers here, one in ICLR with Kong Liao and Shivakumar, and then the other is a manuscript with Zuzic, Wang, and Shivakumar. So this is kind of the high-level question, that can machine learning discover book algorithms? So what does that mean? So machine learning is that kind of, deep learning is that picture on the left, which is, here's this big network, and it can identify that this is actually George Washington. Well, the book algorithms that we know of, like the one I just described earlier, and many such things like shortest path and so on, they kind of look quite different. And also they provide stronger kind of worst case guarantees. So more precisely, the machine learning approach typically trains these systems on stochastic input. So you train a model on certain distribution, and then you kind of know that it's going to perform really well on a new instance, but from a similar distribution, right? While when we design algorithms, at least from the theoretical computer science point of view, we are focused on kind of worst case performance, like that 1 minus 1 over e was you get that no matter what the input sequence is. The question is, can we train a machine learning system to discover worst case algorithms? That's kind of a slightly new question. And if so, first of all, can it solve problems in the worst case? And if so, like, would it solve problems similar to how TCS researchers solve it? So that's kind of a high-level question, and it's still open in its full generality. But we did work on this particular AdWords problem, and there's some nice results. So here's kind of the picture that we start off. So this is Yau's lemma or the Maxmin theorem for designing algorithms. So consider this very big zero-sum game. The row player is the algorithm designer, and the column player is the adversary or the input generator, right? And what's the entry when the row player plays a certain algorithm and the adversary plays a certain instance or input? It's simply the performance of the algorithm on the input. So in the online setting, the entry over there is performance of the algorithm divided by the optimal in hindsight performance. And then what is an optimal algorithm in this framework? It's simply a Maxmin strategy for the row player. That's an optimal worst case algorithm. So the question boils down to, can we find a Maxmin strategy in this big abstract game using machine learning? And so as I said, there's a sequence of 2 papers. And so the first paper, the approach we used was this notion of a universal distribution. So what is this? So if you look at an algorithms paper, for example, that 1 minus 1 over e paper, you have the algorithm, you prove the analysis of it, you say it's 1 minus 1 over e comparative, and then you want to prove that it's optimal. So what you do typically is you come up with a distribution over inputs and prove that kind of no algorithm can do better using kind of your creativity. So that's a hard distribution. That's how we prove optimality of algorithms. And the first approach is, let's just train an algorithm network on those distributions. Those are supposed to be hard. We proved something about them. So what happens if we train a network on exactly those distributions? Would it give us the worst case algorithm? And it turns out that this simple idea actually works. So we do get very good, we do learn networks which are very good approximations for these worst case algorithms, for that AdWords problem, but also for like other problems like the secretary, and the optimal stopping problem, or online knapsack. Yeah. So I won't present the results for this approach. But here is the kind of universal distribution for the online matching problem. So if you remember that zigzag graph with the 2 advertisers and 2 bidders, 2 queries, if you generalize that to the graph on the left, that's an upper triangular graph. So you have an n by n upper triangular graph, and that turns out to be the best, or rather the worst distribution for this AdWords problem. So we train our network on that distribution. Turns out that's not enough, and I'll come to why not. So we also train it on kind of another extra kind of distribution on the right, which is called the thick Z graph, which is kind of a simple Z graph. And turns out that when you train the network on these distributions, then you end up getting something similar to that optimal algorithm, right? But so then we realize that there are some issues with this approach. First of all, you can only use it when you know the hard distribution. Kind of the paper is already written, right? And you're just kind of rediscovering the algorithm. So maybe there should be another approach where you don't know these hard distributions, but you still can come up with some good algorithms. And secondly, there was a more fundamental issue. Yeah, go ahead.
A quick question. So, with those distributions that you showed, I'm guessing that the algorithm that maybe you end up learning is similar to basic balance, but those distributions are for the symmetric case, B matching. How would the algorithm learn about how to balance a sort of non-uniform bits with projects?
Yeah, that's an excellent question, actually. So, let me repeat the question, right? So, in these two distributions, the bits are either 0 or 1. And in that case, there's a more, so there's a special case of that optimal algorithm, which it doesn't have any bits, so it just allocates to the bidder who has spent the least. That's called balance. And Rajan's question is that if I just use these distributions, yes, I can see that it can find balance, but how will it ever find the MSVV, which trades off bidder value? So that's a great question, and I didn't put, there are other distributions you put in here, where there are some large bids and some small bids. So that's, in fact, another, I didn't want to kind of get into that, because unless you know the results, but that's another issue with this problem. You're also, in fact, that's the bullet I'm coming to, that this shouldn't necessarily work. Because, and essentially it comes down to saying that the best response to a min-max strategy is not necessarily a Maxmin strategy. Maxmin strategy is what we're looking for, that's the optimal algorithm. And here the min-max strategy, the adversary, is really just the upper triangular graph with some kind of permutations. There are other algorithms which are best response to that distribution. For example, the balance algorithm, but in fact, even just the greedy algorithm. So you need to augment that worst distribution with other things using your creativity. So that's another issue, right? So now if you think about that, we ended up with the second approach, which is kind of the right approach, which is borrowing kind of ideas from GANs. So in this new architecture, we know nothing about the hard distributions of the problem. We just have two networks. We have the algorithm network, but we also have an adversary network. And they are going to kind of co-trade so that the algorithm network eventually learns the optimal algorithm, and the adversary network eventually learns this hard distribution, not just the hard distribution, but it guides the algorithm towards the optimal strategy. So we call this like the YOGAN architecture, because it's kind of inspired by Yau's lemma. And in terms of architecture, it's inspired by kind of two things. So one is the GAN approach, where GAN is so you have a generator which is generating these hard instance, the generator which is supposed to generate kind of good, good photographs, for example, and then the adversary which is trying to guess. Now, in our case, the adversary is generating these hard instances, and the algorithm network is generating the correct strategies. But from the GAN approach, you kind of train the two networks alternately. And we're going to do some of that. But from a more theoretical perspective, we were inspired by these kinds of zero-sum game solving using experts learning, where the strategy is that the row player keeps a distribution in mind. And then the column player plays kind of the worst input for that distribution, and then the row player gradually changes its distribution to do well against these bad column inputs. And so kind of the way we train is inspired by both of these frameworks, and also uses some extra ideas such as what we call an experience buffer. So I just provided a way, I mentioned that we can use GANs to solve or discover the algorithm. But what does it really mean for a network to discover an algorithm, right? Our algorithm was very simple: give it to the bidder with the highest bid times this function. While a network is this big differentiable structure. So you can't really decode that network to come up with kind of code. We can't even prove a bound of the competitive ratio for the algorithm which it came up with. So what do? Well, we run various scenarios. So suppose a query came in and then these are different bidders and they spent so much money and these are the bids. What would the optimal algorithm do? And what would the network do? And then see if they match in some way, right? We can also run the network on known bad inputs like that triangle graph and see what it does. And for competitive ratio, we can't really kind of prove that there's no input which does on which it does worse than something, but we can train a network against it and give it a lot of time to generate bad inputs and see how it does. So it's kind of an empirical result, but it does actually pretty well, very surprisingly. So the network discovers both these structures of that optimal algorithm. So there's a greedy aspect to it, which is to say that if everyone's spent budget is the same, then I want to give it to the highest bidder. And then there's a balance aspect to it, which is to say that if all the bids are the same, then I'm going to give it to the bidder which has spent the least amount so far. And so these graphs represent some of that. So on the left, we feed the network with a scenario where there are two bidders. They have the same bid, is one each for this arriving query, but we'll fix the second bidder's spend to 2.5, so it spent half its budget. And then the first bidder will vary its spend from 0 to 5. Right? So the second bidder spends half its budget and that's fixed. And then the first bidder's budget spent will vary from 0 to 5 and we'll see what does the network do. So when I guess in this case, bidder zero's budget spent is fixed to 2.5. And as you change bidder 1's budget from 0 to 5, we see that in the beginning when bidder 1 has spent very little, then the probability of allocating to bidder 1 is close to 1. And as you increase the spend on bidder 1, you start allocating more and more to bidder 0. In fact, the crossover point is exactly at 2. And then there's a similar thing for the greedy aspect to it, where you fix the spend of both the bidders to be the same. In this case, it's 3.75 out of 5. You fix the bidder, you fix bidder 1's bid to 0.25, and you vary bidder 0's bid from 0 to 1. And so now they spend the same, and as bidder 0's bid changes from 0 to 1, at the crossover point, we start allocating to bidder 0. And here's kind of even striking picture. So here's the contour plot of what MSVV does. So the x-axis is the bid and the y-axis is the remaining budget. And so these contour lines on the left are those tuples which the MSVV algorithm values the same, because the values, remember, is bid times some function psi of the amount of budget spent. So that's a number. And so each line over there is the set of points which are valued the same. And so the MSVV algorithm basically looks at different advertisers and picks the one with the highest value point. And here's what the network does. And you can see that it's fairly similar. You can also kind of look at the performance against a kind of adversarial networks which try and beat that algorithm once you fix the network now, not in the GAN training but afterwards. And you can see that, basically the orange line is the YOGAN approach, the blue line is the optimal algorithm, and they're both kind of at 1 minus 1 over E. And if you do kind of a fixed training against these fixed distributions, it actually does a little bit worse in this output. Right? And you can go even further. So now we have this adversary network which was used to train in the GAN training. We can inspect that. What kind of instances did it come up with? And so it's hard to kind of really parse these, but if you squint hard enough, then if you're really dedicated, then you can kind of see that you do see some of those upper triangular matrices, you see some of those Z graphs coming up as the adversarial network tries to fool the algorithm. So that was kind of a bit of a curiosity when we started the project, but what does this mean kind of for practice? So we know that machine learning can adapt to real distributions kind of really well. And we could try and solve problems by training networks on it. And what this work kind of suggests is that machine learning can potentially find these more worst case algorithms. And so the idea is that there's a potential to merge these machine learning techniques and worst case algorithmic techniques to work more in tandem. So for example, you could now imagine having robust stochastic algorithms which you could train it on some distribution that you believe is going to occur. But then you also wanted to have some robustness if the query sequence completely changes. For example, in the real world, if suddenly some product becomes very popular, or there's a pandemic the next week, then the whole query pattern will change, and hopefully these techniques can adapt to those shocks a little bit better. Yeah, so do stop me if there are questions before I move on. Yeah.
So, like, when we're trying to build this machine learning algorithm, machine learning network, what equation went behind choosing the network?
Oh, yeah. So, the good news is that we were not machine learning experts. So, we just used kind of very standard forms of networks, something like 5 layers, 100 width, some ReLUs, and we used very standard training methods. So, there was no intuition in kind of building that network either. That answers the question? Yeah.
You had 3 pages earlier that yeah, that's one.
Yeah.
So in terms of the contour, it's in terms of where it stands, there's how sparse is there intuition provided by the GAN approach that, for example, it's denser in the middle, but relative was fast.
On the right hand side, what is it?
And also on the
No, not really. I mean, so this is kind of, we would say, is the truth.
Right.
So this is the optimal algorithm. So it has this form. And honestly, I don't even know I don't remember how we generated these lines, whether they are EP space on purpose or not. Yeah, and then this one kind of just looks similar to that. I'm not even sure.
Basically, it's without the knowing the two solutions, whatever.
Sorry, I mean,
So I was saying that on the other side, it's basically just using the cache to run these zoom pattern and this is true.
yeah, that's all I would interpret. I mean, I do see that it's sparser on the top right over there.
As you mentioned that it doesn't require like a very special design.
Yeah. Yeah, it's possible that with kind of smarter network architecture, smarter nodes, you could get even closer. This was more than
Standard package.
yeah. Yeah, this was learned on just one desktop, nothing, not too much computing.
So, Aranyak, one maybe high-level question. In this case, to sort of get some idea of the MSVV, maybe there are 3 things that the network will need to learn. That it needs to sort of be greedy in some sense, and needs to think about the bits and about the remaining budget. And then we can maybe imagine a function in bits and remaining budget that it sort of needs to figure out. But of course, it won't know that there are these 3 important things. But is it the case also that even if you had an optimal algorithm that's much more complicated for some problem, have GANs been known to even sort of get close in those kinds of?
Yeah, okay, so that's a great question. Um, when I said that we don't give any hints to the network, I was cheating a little bit because the input to the network is bids, it is how much money you spend plus the budgets. Now, one way I can say it is that these are basically the input at every point. So, it's not really a hint, but I do separate those out. So you could say that's a little bit of a hint. Um, and okay, so secondly, these techniques. So as I said in the beginning, right, like the big goal was, can we learn algorithms? But maybe that's like too big a goal, and it's like quite open right now. What we can do is learn some of these online algorithms, and the reason for online algorithms make our life a little easier because there is some state, and then there's like a small amount of input on which you have to make a decision. So usually online algorithms are also kind of concise. And that's why these techniques work. It's a great question. So for example, if we want to see if we can discover shortest path algorithm, like some of these kind of basic offline algorithms, it seems very hard. It's not even clear what kind of architecture you would have.
So people also then build on your work, try to apply and see this for other kinds of online problems?
Yeah, so not really. There hasn't been enough work, and I would very much welcome it. What would be an amazing outcome here? Again, it's a goal which might be too much. Is take even an online algorithms problem, which is not solved yet properly, because we don't know for some problems in scheduling and like that which come to mind. Can we use these techniques to get some intuition about the kinds of algorithms we want to use? Because finally, this is mimicking what an algorithm designer does. You sit down and try and write hard instances and then define the algorithms to beat those instances, but then there'll be some other instance which doesn't work. So you tweak the algorithm further, and that's exactly what this kind of GAN approach is doing. So if there are problems which are open, then this can be a tool for the algorithm design.
So that makes me actually think of this AdWords without the assumption of basic budget being small. Did you manage to actually see what the hard instance is for without that assumption and the being maybe that tells us whether 1 minus 1 over is possible there or not?
Yeah, that's a good question. We didn't even try that.
Yeah, I guess there was a recent breakthrough, so it may be.
Yeah, sure, but that breakthrough is still a tiny breakthrough. So, even we haven't followed up enough on this. It's very kind of an attractive direction. So I have about 5 minutes. Yeah. Okay. So let me not go through the kind of entire talk. I do want to talk about this other question about auto bidding. So we talked about this allocation problem, right? Initially, we had this bipartite graph. So think of that as a centralized approach, and here is a kind of a decentralized approach. So auto bidding is a product that's kind of getting a lot of adoption in the market recently, and as opposed to those tables of keywords and bids, what auto bidding allows the advertisers to. So this is kind of the before auto bidding picture, and with auto bidding, it allows the advertiser to express some high level goals and constraints, and then you have an auto bidding layer which converts those goals and constraints into per auction bids. So auto bidding is an agent for an advertiser. So in terms of that picture, it's a very decentralized approach. Your admission control is through these auto bidding agents, one per advertiser. So what are the different auto bidding products? So we talked about one of them, which is called the budget optimizer. So the advertiser says, maximize my clicks subject to a budget constraint. So that's kind of the simplest auto bidding product. But more interesting products recently have been this product called the Target CPA, Target Cost Per Acquisition. So in that product, the advertiser says, bid for me to maximize my total number of conversions of the sales that happen after a click, subject to an average cost per conversion constraint. So maximize my sales subject to the cost per every sale is at most $10. Okay, and then you can expand that to conversion value as well. So given the time remaining, I think I will just provide the kind of general framework for auto bidding that we provided in this paper. So here's a linear program. Here's an integer program. It kind of captures most of these auto bidding programs. So the objective function has the variable is xi, which is saying that should this advertiser buy the ith ad impression, and then the CTR is the click-through rate. So the objective function basically becomes maximize my total value. VI is the value for that impression. Okay, and then you have a set of constraints C, where so VI is the value for the click, and the set of constraints indexed by C all have the same left-hand side, which is the expected spend, which is should I buy this impression? What is the click-through rate, and then what is the cost per click? That's the expected spend. And then there are a bunch of kind of constraints on the right-hand side, which are constraint specific, but it has this particular form. You can think of B as kind of a budget, but then there are these other constants as well. So it turns out that this formulation can capture most of those auto bidding products I talked about. So if we talk about budget optimizer, I'll take this VI to be just 1. So the objective function simply becomes the number of clicks. And there's one constraint where these WIs are 0, so all you have is a budget. The spend is at most the budget. It can be more interesting like the target CPA, where I take the VI to be the conversion rate. So the objective function becomes the total number of conversions. And the target constraint is total spend divided by the total number of conversions is at most some target T. I want my average cost per conversion to be at most T. But if I rewrite this, then I can take these WIs to be kind of T times conversion rate, and you can capture TCPA also in this LP. So I guess the one question I would go through right now is, suppose an advertiser is opted into target CPA kind of auto bidding product. How would you design an agent to bid on its behalf? So suppose you're given this LP offline, and you knew all those impressions and their costs. Remember that these CPCs come from other bids in the auctions. But suppose you knew all these constants, then you could solve it and say that, well, these are all the different opportunities, but you should select kind of these 100. But that will maximize your conversions, and your average cost will be at most the target. So of course you can't do that. You are still bidding into auctions, and the question is, can you bid in such a way that you will end up with the same outcome? You will end up picking exactly those 100 options for this advertisement. And turns out that the answer is yes, and it depends on some underlying properties. So here's that same linear program over here. And again, we leverage duality. So we write the dual, and we won't get into what kind of the dual looks like, but if you look at kind of the complementary slackness conditions, it says that you want to take all the items where the cost per click is at most this kind of formula over here. What does this formula have? It's got the value of the impression, which in the TCPA setting is the conversion rate. It's got some of these constants, which has kind of the target inside it for this product. And then it has these alphas. The alphas are the optimal dual variables. So if you had a handle on these optimal dual variables alpha, then essentially you want to take those items whose cost is less than this right-hand side for that item. And so then that's really good news, because now you can implement that in the auction by simply bidding this right-hand side. Because if you bid that right-hand side, you will win the auction as long as it's a second price auction, because the cost will be less than your bid and you will get the item. So it turns out that you can implement that optimal selection by this kind of very uniform bidding formula, as long as the auction is truthful. So the theorem is that if you had a handle on the correct values of these alphas, then that bidding formula is optimal if and only if the auction is truthful. Where do you get the handle on these alphas? So again, it's kind of similar to that previous problem, where if you had some kind of stochastic input, then you could learn those alphas over time. Practically, you would learn it from past data. And kind of theoretically, you could also employ these experts' algorithms to learn these alphas. Let me just go through this second kind of thing just to complete the picture. So I showed you a way to bid optimally for one advertiser. And that bidding needed you to know the cost per clicks in those auctions. Now, where do those cost per clicks come from? Well, they come from all the other advertisers' bids. So what happens if all advertisers deploy your auto bidding product? Now, there's a circularity because each LP depends on every other LP. So it's pretty confusing to think about, but we think about it in equilibrium. So everyone is bidding in such a way that given everyone else's bids, you are bidding optimally using that formula. And when that happens, we want to know what's the quality of that equilibrium. Like, could it be that kind of everything goes down to zero and we make all the bad allocations? How good is the matching which comes up in that equilibrium? And well, I won't get into this for lack of time, but there's a notion of price of anarchy, which is that is the worst case over all instances of the optimal efficiency you could have divided by your efficiency in equilibrium. The optimal efficiency is simply to give each item to the one with the highest VI. But when you go through the bidding and the auction, you may not necessarily do that. So how much do you lose? And basically what we could prove is that for that very general auto bidding problem with any number of constraints, that price of anarchy in a truthful auction is 2. So it's no worse than 50%, and in some instances it could be as bad as 50%. I think for lack of time, I should stop here. Thanks very much. I'll take more questions.
Thank you, Aranyak. Let's